Okay, welcome to some new slides on one topic, functions, that you know and love already from math, and then another topic, relations, which technically you have learned about. You just haven't been calling it that word before, but you know many relations by now. So let's get started and talk first about functions. So this is more like the mathematical kinds of functions, but technically computer science functions are similar. So we have that a function f that maps elements of a set x to elements of a set y. So we had to study set theory to get here, right? Because sets map things. They map inputs to outputs. So we're going to say that the inputs are part of set x and the outputs are part of set y. It ends up being a subset of x cross y. You really are making a Cartesian product. You're associating a bunch of pairs, right? You're associating like x's on the left with y's on the right. So that's like a coordinate, and you can describe functions in that way. Okay, so for every x in your input set x, there is exactly one y in your output set for which you have in the function, because the function is a set, you have the pair mapping x to y. Okay, so you can define a function f like this. You can be like, all right, f is equal to a bunch of pairs. It's equal to x1 mapping to y2, and then we'll say that x2 maps to y1, and then that x3, let's say that maps to like y4 or something, and I'll draw this in just a second. But you've got x's being mapped to y's. Okay, that's essentially the idea of functions. And if you just label like every input to every output, that is essentially describing a function. All right, so functions are just sets of pairs, and x, this input set, it's called the domain of f. You've heard that term before, I'm sure. So x is the domain, it's the input, and then the output is called the output set is called the target set or the codomain. Okay, so that's what's going on there. It really is just a set of pairs. So let me draw this function. So here's like the set x, and here's the set y. To be a function, you better map every element of your x set, of your input set. So here's, if this is a complete function, then x1, x2, and 3 better be the only members of this x set. All right, so that's x. And then y. Y could be bigger. As long as you're mapping every x to some y, you're good to go. So y could be bigger. Maybe there's y1 through y4. So we got y1, y2, y3, and y4. And you can map these around places, but again, x is called the domain, and y is called the target or the codomain. You may have heard of range. This is not a range yet. I'll get to that. Okay, so x1, that's mapping to y2, we say. So you can define a function just by listing out how it works. So x1 maps to y2, x2 we said maps to y1, and then x3 maps to y4. So something like that. And it's okay if we skip y3. That's fine. It's still a function. All right, so it's really just a set of pairs. You can draw it like this. It's totally fine. And f better map every set of that, every element of that initial domain set somewhere. Okay, so if f maps an element of the domain to 0 elements, if there's an x4 here that isn't going anywhere, like off into the ether, it's not going anywhere at all, then it's not a function. All right. And then also, if it maps an element to more than one place, like x3 can go, like say that the function takes x3 to y3 and y4 at the same time, it's still not a function. All right, so that means your function is not well defined if that ever happens. So it's got to map exactly one input to exactly one output, and it maps every single input somewhere. Okay, so if it doesn't do that, if it maps an element to 0 elements of the target, or if it maps an element of the domain to more than one element of the target, then it's called not well defined. Otherwise, it is well defined. It's a normal function. Okay. Range, you've probably heard that term before. This is what the range means. It's not the same as y. It's not the same as y. It's all the pieces that are being hit by the function. So it's all the pieces that are being hit by an arrow. All right, so the range of f is the set of all the y's that are part of the function, all right, that are being mapped by the function. So in this example, the range of the function f, this is our example function f again. Sorry, I should maybe say that f, there, this whole thing. This is the function f, all those arrows. The range of f is all the y's that are being hit. So y1, y2, and y4, not including y3, okay? And that's not equal to the codomain, which was all of y. Okay, so that's a key difference, and it'll get more apparent as we give more examples. So codomain is not the same as the range. Okay, so that's a start. Let's have some more terms, because of course with every new topic comes more terms, even though we've learned about functions before. So this is how you write that functions have a certain domain and a certain target or codomain. You say f, and then you put a colon. It's like the type of the function in a sense. It takes these kinds of inputs to these kinds of outputs. So let's say that f is a function on integer, so it takes an integer to another integer, all right, where this is its definition. It takes the input x, and it computes the absolute value of x, where x was an integer. Right? The domain is on integers, and it's computing whole numbers as well, because that's the absolute value of an integer is still an integer. So the domain, we say, is all the integers, right? The target is all the integers. That's what it's meant to be. But then the range is all the pieces of this function being hit, all the y's, all the pieces of z that are actually being hit by this absolute value, which is not all of z. So let's figure that out together. So let's see. F of like -42, for example, this function will give back the absolute value, which is positive 42. If you input f of 3, it keeps it at 3. F of 0 is 0, but do you see, like here's the number line, this is 0, like it's going to map -1 to +1. And so it's like going to do this. Boop. And then every number that's already 0 or bigger, because we're working on integers only, they're all going to be mapped to themselves. So 2 is going to be mapped to itself, 3 is going to be mapped to itself, and any negative number is going to be mapped way over here. See that? So that's what's going to go on. So that's -2. They're all going to be mapped to the positive side. So all the values being hit, all the output values being hit are 0 and bigger. You see that? So the range of this function, the values being hit by this function, the outputs, are only non-negative numbers, and that is the set of the natural numbers, right? 0 onwards, all those whole numbers only. So that is a function f, and we say you have to give its domain and its codomain in addition to its definition and how you compute it, because this is very different. This function f is very, very different to this function. Let's say that g is a function from real numbers to real numbers. It takes inputs, its domain is real numbers, its target or codomain is real numbers, and g of x is equal to the absolute value of x again. This one is a different function to this one. Do you see that? Because it takes and it outputs different things. Like f is not allowed to take pi. F can only take whole numbers, whole integers. G can take any real number, so g can take pi. It can take negative pi, in fact. Like you can pass along negative pi to g because a real number can have decimals like that. And it will give you back positive 3.14, which is another real number, right? Another number with decimals. So these two functions are not the same. You see that? That's important. Okay? Two functions are the same, if and only if they have the same domain and target, and their values are equal. All right? So even though this is computing the same thing, these functions are not equal because they don't have the same domain and target. All right? So that's required. And then for every input element, because you know that the input elements are the same because the domains are the same, the output element value better also be the same. Okay? So that's called functional equality. That's what it means for two functions to be equal. They better have the same domain and codomain, and they better have the same output values for each element of that domain that they share. Okay? That's the idea. So that's a bunch of new terms, and you try now. So here's a piece of the book, and I'd like you to go through both of these functions. Remember, they're being written in this way, like you got the x, the domain on the left, codomain on the right, and see if you can figure out the domain and the range of f and g. Okay, the codomain is just implied to be everything over here, but what's the range? Is there a difference? And also tell me if they're well defined. So here's the function, or here's the definition of well defined again. So give that a try, and then I'll show you the answers. So all right, F. F is mapping stuff from the left to the right. So domain, same with G as well. Actually, the domain of both F and G are just the things that are being mapped, the things on the left side of an arrow. So A, B, C, and D are both domains for F and G. So the domain of F, everything on the left side of an arrow is the values A, B, C, and D for both F and G. So the domains are the same, if they are functions at least. So there's that. What about the range of F and the range of G? So the range is just anything being hit by the right side of an arrow. So the range of F appears to be W, X, Y, and Z, and the range of G, do you see how it's only hitting those things? So it's W, X, and Z only for G. So the range of F is going to be W, X, Y, and Z, all of them. And the range of G is going to be only the values hit, so it's W, X, and Z. Let me write a better X. There. So there's one difference. And now also are these well-defined functions, all right? So any well-defined function better map the domain elements to exactly one output element. So let's see. Dun, dun, dun. Is F mapping each input to exactly one output? This one is, this one is, this one is, but this one, it's being mapped, B is being mapped to two different things under the function F. And so that means it's not well-defined. Right here is the reason it's not well-defined. Okay, can't have both of those. So it's not well-defined. And then G, does it take every input to exactly one output? Boop, 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 boop. Yes, yes it does. It's okay that it doubles up, like the absolute value function. It takes both -1 and +1 to the same output of +1. That's totally allowed, as long as every input is being mapped to exactly one output. So G is well-defined. So that's beautiful. Okay, hopefully that's making some sense. Let's try another. So here are two more functions. So here is F. It's a function of pairs of integers to a single integer. And here's the definition. It takes two things, right? F of x and y. Its output is the absolute value of x plus y. So do the addition first, then the absolute value. And then G is a function with a similar domain and codomain, so that was a requirement for equality. So they might be equal. So again, it takes a pair of numbers to a single integer. Pair of integers to a single integer. So the inputs, call them x and y. The output is do the absolute value first and then add them. All right? So you tell me, does F equal G? And here's what it means for two functions to be equal. They better have the same domain and target. These ones do. And then also for every input value in the domain, the outputs better match. So do they equal each other? So the easiest way to check this is to try a bunch of options, but your two requirements for functions to be equal is that they better have the same domain and codomain. And that checks out for these guys. And then also the functions need to agree on every input. Or in this case, pairs of inputs. Functions agree. And both of those need to be true. So let's see. If you think about it long enough, there's a way to get these to be different, actually, right? What if you do f of -2 and +2 and g of -2 and +2? So same inputs, they should be mapped to the same outputs. But f is going to do the plus first, so it's going to do -2 plus 2, and then it's going to take the absolute value. And that answer is 0, right? Because it makes 0, and then the absolute value is the 0, keeps it 0. And then this one does the absolute value first, and then adds. So -2 absolute value, +2 absolute value, then add them. That's, of course, equal to 4. And those are not the same. So the functions do not agree. And so that does not check out. And therefore, the answer is no. These functions are not equal. Okay? I hope that makes some sense. So that's what's going on there. Let's keep on talking about some more definitions now. So another thing that you can ask for a function on numbers is to round in different ways. So here are some fancy kinds of rounding. So you've actually seen one of these before, at least. There's a function called floor. This is a very cute metaphor. The floor function takes a real number. This is a function that takes real numbers to integers. All right, and it rounds it down. It takes that real number to the nearest integer in the downward direction, like it's shoving it onto the floor, which is so cute. And so this, to spell it out, it looks like this. Floor, it takes a real number, outputs a whole number, an integer. So it could have decimals. It gets rid of the decimals. It rounds it down to the nearest whole number in the downward direction. So the nearest number that is smaller than or equal to the number. So where floor of x is the largest integer y, such that y is less than or equal to that input x. So it's got to be smaller. It's like pushing it down onto the floor. And the cute little syntax for that is you put some angle brackets, but you chop off the top part. You only leave the floor. So that is that's what it means to take the floor of x. Okay, so that's the syntax for it. And so you write it like this. It's the floor of x. It's going to take x and it's going to round it downwards to the nearest whole number. It's going to chop off the decimal places. So actually, floor is what you get when you do a static cast in C++. If you take a static cast of a double and you convert it to an int, like 42.5, it's not going to round it up or anything. It's going to round it. It's just going to chop off the decimals, and that's what the floor does. All right, that's what the floor function in math does. So 3.14, the floor of that is just 3. It's the nearest integer that's smaller. 42.5 is, of course, 42. Right, so the nearest integer that's smaller. It's not going to round to the nearest number. It's going to round to the closest number that is smaller, all right, or equal to. So like the floor of 394, it's already a whole number. It doesn't need to get any smaller. So there's no rounding that really needs to be done there. So that one's still 394, but every one of these other ones, it chops off the decimals. So this is like 394.0, I guess. It still chops off the 0.0. So that's the floor, and then the opposite of that, again, very cute, is ceiling, like you're pushing the number up to the ceiling, and that rounds a real number up to the nearest integer that's bigger than or equal to it. Okay, so again, the ceiling function takes a real number, outputs a integer, and it works like this. Ceiling of x is the smallest integer that is greater than or equal to the input. All right, so again, the notation looks like this. It's like you're drawing the angle brackets, only the ceiling part, right? No floor down here. Ceiling only, which is super cute, and it's going to round up, okay? And so here are some examples, like 3.4, what's the ceiling of that? It's the nearest whole number that's bigger, so it's 4. It's going to round up always. 42.5, round up always to 43. See that? So that's going to be 43, and then 394 is already a whole number, so the nearest number, the nearest integer that's greater than or equal to that input, 394, is still 394, right? So that's how that works. That's floor and ceiling, and these are important in computer science. Floor, for example, is super important because that's what the difference is between integers and doubles. That's what happens when you convert. You're really taking a floor. All right. So with that in mind, let me get you used to this idea and this notation of floor and ceiling. So here's your question. A baker is packaging cookies for sale in boxes of 8. So every box has 8 cookies in it. And he has a total of y cookies that he baked to put into boxes. It may not be a multiple of 8, though. So how many boxes can the baker sell? Try to formulate your idea in terms of floor or ceiling. And remember the definitions and the notation. All right, so if you have y cookies and each box holds 8 cookies, how many boxes are you allowed to sell if you can't have less than 8 cookies in a box? So, if you think about this long enough, like if y was equal to 24, if you had exactly 24 cookies, then you could make, 3 boxes, yeah, because 8 times 3 is 24. You could put those into 3 separate boxes and call it a day, and you've used all your cookies. But if you made 25 cookies, what happens then? You can't have a box of 1, and you can only have 8 in a box, and so you can still only make, you see, 3 boxes of cookies. You're going to have 1 left over and you can't put it anywhere. So maybe you waste it, maybe you eat it yourself or something. But you see how it's essentially dividing by 8 and it's rounding down. See that? So the answer is going to be take your input cookie number, divide it by 8, and whatever answer you get, you're going to chop off the decimals because you can't have fractional boxes of cookies. You're flooring it. Does that make sense? That's the idea. If your y over 8 is like equal to 1,000.9999, you still can't make that 1,001th box, can you? So you're forced to floor the answer. If you don't have enough cookies to fill a new box, you can't make a new box. So that's what the floor is telling you. And I hope that makes enough sense. It's rounding down. You're forced to round down. You can't just make like 3.1 boxes or something. It's impossible. You can only make a box of 8. So I think that's a good little question to get you used to that. More terms. Of course, we're not done with terms. We never are. So we say that a function x to y that takes inputs x to outputs y is called one-to-one or injective. That's like the pretentious Latin root way of saying one-to-one. If this implies this. If x1 not equal to x2 implies that f of x1 is not equal to f of x2. All right? So you've probably heard this term before, one-to-oneness. This is the logical definition of it. It involves an implication. All right? Another way that this is saying something, it's saying that f maps different elements in x to different elements in y. It's making sure that everybody's hitting somewhere different. All right? So informally, if you want to like think about this long enough, draw a bunch of pictures, maybe take the contrapositive if you want to. Informally, this is trying to say that f never hits the same place twice. Okay? So here's an example of a function that is one-to-one. So let's say the input's on the left and the output's on the right. It's okay if the size of the codomain is bigger. This is a one-to-one function. It takes every input to a different output. So this function is one-to-one because different x's, like these two are different x's. You see that their outputs are also different. These two are like different x's. Do you see that their outputs are also different? That's what it means to be one-to-one. One input has one output associated with it. There's no way to go, nobody shares. Like this one, if I made this one also go here, for example, that means you got two inputs go into the same place. That would not be one-to-one. Okay, so let me draw that. So here's a function that is not one-to-one. Boop. You're kind of forced to not be one-to-one if you have a smaller codomain, for example. So let's say this is your function, and let's call, let's call this x, y, and z, and then a and b. So you see how the function on input y goes to b, and the function on input z also goes to b? So this is not one-to-one because this doesn't hold. We have that y is not equal to z, right? But we do have that the output is the same. It's not upholding the end of the bargain. It's not getting the conclusion right. But f of y is equal to f of z. And so that makes the whole implication false. So sad day. We don't like that. So that's that one. Okay, so that's one-to-one, or injective is another way to say that. You're never hitting the same place twice. We then also say, you've probably seen this one before, I remember this one from like high school and stuff. So a function from x to y is called onto, or surjective. That's the fancy Latin root way of saying onto. It's onto or surjective if the range of f, so that's the things being hit by inputs, is equal to the entire target y. It's surjective if the whole target is covered, right? For every y in your target set, there is an x, such that f of x gets you to that y. It means it's being covered. It's hitting the entire output codomain, or target. So that's what it means to be surjective. That's when the range is equal to the target, okay? So informally, f hits every element of the target / codomain, okay? So that's finally when those two terms mean the same thing. So here's a function that is onto. Let's have more inputs than outputs again. Totally fine. So this function wouldn't be one-to-one, but it's totally going to be onto because it's going to hit every single, let's say this one goes to here, because why not? Let me draw that better. So have this one go to this one can go here again, and then this one will hit this one. So do you see how every element of, let's pretend that the right-hand side is the codomain, every element is being hit. So that means it's onto, all right? A function that's not onto is like this one. It's not being hit properly. So if I just redraw that in maybe a different way, do you see how if you assume that the right-hand side is your entire codomain, it's not going to work out. 1, 2, 3, 4. So this one goes here, and then these bad boys, let's say you go here and you go here. This one's left out. See that? It's not hitting this function is not hitting every element of the target or of the codomain, so it's not onto. Okay? The range is not equal to the target. So that's that one. So these are important terms to have because they allow you to take the inverse if you have both. All right? And we like to have invertible functions. So a function, if it is both one-to-one and onto at the same time, it's called bijective. All right? Bijective, if it's both injective and surjective, it's then bijective. And it's also just called invertible, or a bijection, or a one-to-one correspondence. So there's a lot of different terms for this. And so let me show you a function that is bijective. So let's say this is my input set x. Boop. And then if you think about it long enough, the output set y better be of the same size. Doesn't have to be the same set, but it better be of the same size. This is both one-to-one because every input x is going to a different output y, and it's also onto because the entire codomain y is being hit by somebody. It's the target of an arrow. So this is a bijective function. And then once you have a bijective function, then it has an inverse. You can go backwards. You can take, instead of going from x to y, you can go from y to x along f inverse. Okay? So the inverse of a bijective function is just like you switch every one of those tuples. You switch the inputs and the outputs. So it's if you had x comma y and f, just make f inverse be y comma x. The input is now the old output. Okay? Just swap the input and the output. Because here's what you can do now. You see that you could go backwards. And it's unique. You can always go from this guy. You can just rewire this. You can always go backwards to the x that took you to that y. You see that? That's what you get when you are bijective. There's always a way to go backwards and undo yourself, to invert. And so, just to spell it out, this is the inverse. It's the dotted lines, but I'll draw it again. This will be your inverse, where this is x and this is the y set. It's now, the inverse is now a function from y to x. Y is the domain. So it took you to the x that took you to that y, essentially. Kind of undid the function call. So that's the inverse of f. Okay? So you swap them. And so my challenge for you is to think about why you need both. Why do you need it to be both one-to-one and onto? Like what happens? What breaks down? Why don't you get an inverse when it's not one-to-one? And what breaks down when it's not onto? So think about both of those. I think you'll come up with the answers pretty quickly. But that is a very good thought experiment. And now here's another question for you. So now that we know about inverses and one-to-ones and onto and bijectiveness, see if you can find the inverse of the following functions. All right, if the inverse actually exists and is well defined. So first of all, to have a function, it needs to be invertible first. It needs to be both one-to-one and onto. You better check that. All right. So here's a function f. It takes integers to integers. All right. And f of x is equal to x plus 3. All right. So it's going to take integer x's to output x's. All right. So that's f. See if this function f is invertible. If so, find its inverse. And then see if this function g, which also takes whole numbers, integers to integers, and g of x is defined to be this. G of x is equal to 2x plus 34. All right. See if it's one-to-one, see if it's onto, and if it's both, that means it's invertible. It has an inverse. And see, therefore, what it is. Figure out what it is. Give it to me in math. Okay? So, assuming you gave that a good try, if you think about it long enough, a is pretty invertible. This function f. Because what is f doing? Like here's the input z. It's an infinite set, of course, but who cares? We can still kind of draw it. So it's taking input z's to output z's. How do I want to do this? There. So here's like infinite set. Let's draw a few examples though. So like it takes -3, -2, and -1 as inputs. 2, what does it do to them? This function f, it adds 3. So it's going to bring it to positive 0, or not positive 0, just 0. Then, so -3 along f Adding 3 goes to 0. And then negative 2 goes to 1. And then negative 1 goes to 2. And just kind of goes onwards like that until the end of time. So that's the function f. Is it 1-to-1? Yeah, it sure is, right? It's mapping each different element in the domain to a different element in the codomain. It's never overlapping. That's fine. They're always hitting somewhere different. Yeah. And then also, what else do you get? It's onto because there's always some element over here that's being hit. It's just the 1, 3 before it. You see that? So that's my hand-wavy argument there for being both 1-to-1 and onto. So then that means that the inverse exists. This is a bijective function. So what is the inverse of this function? Well, the way that you solved it in like a math class was you just flipped them. You said like replace x in f of x. Or replace x in y when you were learning it in school probably. But let's say, okay, so f of x, that turns into x. And then you solve for the thing again. Let's turn x into like f inverse. F inverse x plus 3. So that's like me swapping x and y if this was like y. That's how we solve for inverses. At least that's how I was taught. And so if you solve for f inverse of x now, you get that f inverse of x is equal to x minus 3. So that's the inverse. That will take you back to the x that got you here. So like 2 minus 3, that's the negative 1. You can turn this around, right? You can go backwards. Boop. You can always go backwards because it's both 1-to-1 and onto. So that's your inverse for this function. And now the question is about this function g. Is it 1-to-1? Is it onto? Okay, so I do believe it's 1-to-1. All right, it's totally 1-to-1 because, like, let's see, g of 0, for example, is being taken to 34. And g of 1 is being taken to 36, right? It's like every x is going somewhere different. It's like the next 2, the next 2, the next 2, right? So it's hitting somewhere different. But now the question is g onto? That would imply that there was like z, right? Every element of z needs to be hit. But do you see how this one's kind of like skipping over 35? That's a key thing to notice. So if there was an inverse, if it existed, what would g inverse of 35 be? Like, how would you get it? Like, you can pretend, you can do this game again, but it's not going to work out. Let me show it to you. So if you swap x and g inverse of x, the side is x now, 2 times g inverse of x, like me swapping x and y, plus 34. So solving for the inverse, you're going to see that there's a problem here. So this is like, if you solve, this becomes that g inverse of x is equal to x minus 34 over 2. And so, like, if this was a normal function, it's saying that, like, if you run it, g inverse of 35, right? Because you see that 35 is being skipped here. Like, what was the input that would have taken you to 35? Well, it's equal to 35 minus 34 over 2. This was the input that you needed to hit that number, and that's equal to 1/2. But this is a function that only takes whole numbers. So 1/2 is not a whole number. It's both a real number and a rational number, but it's not a whole number. It's not an integer in the set z. So that means it's not going to ever be hit. We're never going to hit 35 with this particular g. Do you see that? We're never going to hit 35 if we're taking only integers, because we would need to have passed 1/2 to hit 35. So that means we're never going to hit all of the target. Okay, does that make sense? So therefore, this function g is not onto. It may be 1-to-1, but it's not onto. It's not hitting everybody. And so that means g is not invertible. It does not have an inverse. Okay, so please yell at me if you have any questions about that, but that's how you look into that kind of stuff. All right? So it's really nice to have an inverse, but sometimes you just have to give up because you don't. Okay, so that's that one. Let's see here. Don't know why that's doing that, but here, let's talk about composing functions. That'll be the last thing. That's actually part of this little meme picture. It's talking about function composition, like something after something else. You see that f composed with g makes a pineapple pizza, but g composed with f makes a pineapple slice with pizzas on top. So that's the cute meme, but you'll understand that after, hopefully, this slide. So function composition, hopefully you've seen this before. It looks like this. It's a little circle. and you read it as G after F, or G composed with F, because you do F first still. You read it a little bit backwards, that's okay. It's a way of combining functions to make a new function, a new combined function. And this is a composed function. This G composed with F, or G after F, means to apply first F, then G. So G happens after F. So let's see, how do I want to show that to you? So like this is essentially it. It's defined like this. G composed with F, that's a new function. If you run it on an input X, what it does is it computes, it does F first, and then it runs G on that result. So that's how it goes, okay? So that's how that works. And so these functions do need to align in a certain way. Like F needs to go from like X to Y, and then let's say that F goes from X to Y, then G needs to take Y's to some other place, maybe to Z or something. You see how they have to align like that in terms of domains and codomains? So that's important. So let's see, here's an example. So let's say that F is a function from integers to natural numbers. So that's, let's define it to be the absolute value function on integers. And then let's say that G is a function on natural numbers that goes to either true or false, goes to a Boolean, goes to that set. And G of X for some input natural number is like, is that number greater than 2, true or false? And so their composition, G after F, that's the only way you can do it, by the way, because you got to do F first to make an N, and then G works on N's. So G composed with F on input -5, what do you get? So first of all, these needed to align. You first do F, right? You do F of -5, and that gives you +5. So that's a natural number, right? And so that, like, this turns into +5, and then you run that. You run G on that answer, on +5, and that gives you back, well, is +5 greater than 2? Yes, it is, so true. So the output of this entire composed thing is true. So the input was -5, the output is true. So the composed function takes an integer to a bool. Okay, that's what's going on there. So let me try and show that to you. So F was a function on integers to natural numbers, and then G took natural numbers to true and false. And if you compose G after F, then you're going to do F first, right? You're going to take as input integers. Sorry, that's too thick. Let's make that smaller. You're going to take as input integers, and your output goes all the way to true and false. See, your input was that, and it went all the way to the output, because the intermediate step was that natural number. So it went to here, so it had to align. These functions better align, like from here to here. These better be the same, so that you can combine them, and your composed function goes straight from your domain of the first function to the codomain of the second function. Okay, that's the idea. So this G composed with F is a function from integers to bools. All right, so that's that one. So let's do a couple of these examples, and then I'll talk about identity. So let's say that F is a function from A to B, and G is a function from B to C. So G to F, what's like the type of it? What's it going to take, and where's it going to take it? So this is G after F. So F goes from A to B, and so you do that one first. You took an input A, you got a B, and then you ran G on that B. You took that B to a C. So in total, this composed function it starts with F's input, took that A, made a B, then you ran G on that B, and it gave you a C. So the final output is a C. So this goes straight from A to C. See that? Then what about F after G? This is doing G first. It would take as input what B takes, or what G takes as input. So it would take a B, and then what would the output be? Well, once you run G, it gives you a C, and then you're supposed to run F on whatever that C was, but they don't line up. See that? So this won't work out. This is not defined. Does that make sense? So they do have to align in a certain way in order for it to work out. Yeah, so with that in mind, there's one last kind of function that I want to talk about. It's just a default function. It's called the identity function. We'll say I sub A on a set A just maps every element to itself. So the identity function on the set A is, of course, going from A to itself, because it's taking an input right back to itself. It's still in the same set. So the input is the output set. So it's from A to A. And so the identity function on the set A of some element just goes right back. The output is that original element. Okay, so that's how you define the identity function. It's essentially this function. It takes the set to itself, and it's always aligning things. Like this element goes to the same element in the output. If this is the input set and this is the output set, and they're the same set, everybody goes to themselves. Okay, so as examples, like the identity function on integers of the number 5, the input is 5, the output's 5. Just like gives itself back, identity. And then the identity function on, I don't know, let's stay with zland. Identity function on integers of the number 42, the output is the same as the input, so it's still 42. Okay, so it just takes a thing and gives you back a thing, the same thing. So that's that. And now you know its domain and codomain's the same set. So see if we can come up with the types of these functions. What's their input, what's their output? All right. So remember the f goes from a to b, and then I of a, the identity function on the set A, goes from a to itself, a to a. So, all right, the composed thing is f after the identity function on a's. Well, it takes as input whatever this right thing takes as input, so it takes an a, which produces an a, then you feed that a to f, and it gives you a b, and they do align. It does work out, and so this goes from a to b. See that? So, and actually, you can say what this function is equal to, because f composed with the identity function on a, it looks like this, right? If you apply that to some element, that's equal to, well, first do the identity function on a of a, and then apply f to it. But the identity function on a just gives back a, the same a that you gave it, so this is equal to f itself. So this is equal to the original function f. Okay? It's really equal to f. So its type is from a to b, sorry, so colon a to b, but the answer is, if you put an equal sign here, it's really equal to the function f itself. See that? So that's actually an equality there. That's pretty cool. And then what about this one? Can you do this? F again goes from a to b. If you do that first, and then you apply this identity on a's to it, does this work out? Well, it takes an a, produces a b, and then you're supposed to run this on a b, but it takes an a. So that won't work right. So this is not a defined. This is not a good function. It does not make sense to want to compose in this way. It does not work. Right? They have to align. All right, what about this one? Is this one defined? Is this equal to something? So again, this is, it's going to run this first on some input element of whatever domain it is. So it's going to take b's to b. So it's going to take as input a b, gives back a b, and then it's going to run f on that output b, but f expects an a. So again, they don't align, because you need always that this output type corresponds to this input type. This output type needs to correspond to this input type. So this one didn't work out, and same here. This output type does not correspond to this input type. So, not defined. But this last one should work out. Do you see how f goes from a to b? So this function is going to take an a and give back some element of b, and then this, we're going to feed that through the identity function on b's, which takes a b, gives back a b. Finally, we get the output, again matching the input here. And so it's going to take that f and map it to something, map it to f of a, and then it gives back ab, and the identity function on b's keeps that same function and gives it back. It keeps that same output and gives it right back. So this is again equal to f, equal to the original set f, or original function f, sorry, for the same reason as why this one was also equal to just you could have called f on that value. Okay, so that's that example. That's composing functions, or function composition. You try. So let's say the domain and the target for functions f and h are z, so just naturally they're going to correspond. It'll work out if you try to compose them. Here are two functions. Here is f of x, 2x plus 3, and here's h of x, x squared plus 1. So you know, because they're going from z to z, both of them, that their composition is, like, it aligns properly, so the composition exists, it is well defined. See if you can come up with an explicit mathematical formula for f after h. So do h first to some value. Try to plug them in here and see if you can come up with a mathematical formula for what happens when you do f composed with h. Try to, like, get rid of all the f's and the h's, like only have math at the end. So can you solve for that? So, all right. F after h. f composed with h. If you run that on something, some element x of z land, of integer, you get, well, this is just doing f after doing h of x. And, well, what is h of x? H of x is defined to be x squared plus 1, so it's f of whatever x squared plus 1 is. And if this is the input to f, that's your new x, then can you apply 2x plus 3 to that? It's going to take its input. What f does is it takes its input, doubles it, and adds 3. So if this is the input to f, it's going to double it and add 3. See that? 2 times x squared plus 1 plus 3. And then, so we can solve for an explicit formula here. This is equal to 2x squared plus 2 plus another 3, so plus 5. So that's your explicit formula for f after h. So f composed with h of x, that's defined to be, first of all, it's a function from z to z again, and it's equal to 2x squared plus 5. Okay? I hope that makes some sense. That's the idea. That's what's going on there, and hopefully it is all coming back to you. Some of this stuff you should have seen before, but we're just studying it harder, and we're also introducing sets into the mix, because that is how math is defined. We have to play by all the mathematicians' rules. So that's functions in a nutshell, and that's where I want to stop for the day. We'll come back and we'll talk about relations next. So I'll see you then.